lightning protection system and earthing. So before entering into the topic, let us put a small introduction about CIKIT. CIKIT was incorporated in 2018. So even though it is a 6 years old company, we are having an experience of more than 17 years in this field of lightning protection and earthing. And our specialization is we are providing end-to-end solution for both lightning protection system as well as this earthing. And our one more specialty is we are providing customized solution rather than going for a generalized solution. So customized solution in the sense, if we are working with any specific field, we will be referring to the standard that are specific to that particular industry. For example, if we take solar, so for solar recently, one more standard called IS 17978 was published. So when we are working with solar, we will be referring to the particular standard instead of referring general standard like 62305. So we are providing customized solution rather than going for a generalized solution. And if we are providing end-to-end solution, which includes performing site analysis, site survey, performing risk assessment calculation, designing of lightning protection system, material supply, installation, maintenance of the existing system, and auditing of the existing systems as well. So these are our specialty. As I mentioned, these are some of the standards which we refer for earthing as well as this lightning. So if you take this lightning protection system, the risk analysis is considered as the first step of designing. So we cannot generally mention that all the buildings and structures require lightning protection system. So first is we have to determine whether lightning protection system is actually required for the particular site or not. So if lightning protection is required, then only we have to determine what will be the suitable level of protection for the particular site conditions. So the first step is we have to determine whether lightning protection is required for the site or not. So that can be determined by performing this risk assessment calculations. So these are the commonly asked questions by many people related to the risk assessment. First one is whether all the structures require lightning protection system or not. Second, how can we select the suitable level of protection? And third one is how can we use the same level of protection for buildings at different locations? Like for example, if I take the same building of height 15 meters, if the building is located in Chennai, Mumbai, and another same dimension building is located on Bhubaneswar, whether the level of protection will be the same for the buildings of same dimensions in different locations. So these are the common asked questions by many people. So in this webinar, we will be discussing about how the risk assessment is calculated and what are the parameters that make an influence on performing this risk assessment calculations. So we have already performed a separate webinar about this risk assessment calculation alone, and we have uploaded it in our YouTube channel. So you can refer to that particular video for more details about this risk assessment calculations. So in today's session, I will be concentrating only on the points that are required for performing these calculations. So if you take this risk assessment calculations, we will be evaluating the risk due to lightning on that particular site conditions. So standard has mentioned about 4 different risks. So the 4 different risks mentioned by the standard are risk of loss of life or risk of injury to human life. Second one is risk of loss of service to the public. Third one is risk of loss of cultural heritage. And fourth one is economic loss. So these are the 4 losses we will be discussing about this risk assessment in today's session. And the corresponding sources of lightning there are mainly 4 different sources that causes damage to the buildings. So we have explained about the sources, damages and losses in detail in the separate video. So since we have to discuss about this lightning protection system designing and earthing also in the same webinar, I'm just skipping this topic. So there are 4 different sources that relate to the damage, that are flashes to the structure. Second one is flashes near the structure. Third one is flashes to the lines, and fourth one is flashes near the line. So these are the 4 sources that causes damages, and the 3 damages are injury to human beings, physical damage to the structures, and third one is failure of electronic equipments. So in risk assessment, we will be calculating the risk due to this particular lightning on the particular site conditions, and what are the preventive measures that we can take for reducing the losses due to this lightning. So that will be the theme of this performing risk assessment calculations. So there are 4 risks mentioned by the standard 623 part 2. The 4 risks are R1, R2, R3, R4. So in R1, the R1 is comprising of different risk components. RA, RB, RC, RM, UV, WZ are separate risk components. And R1 is due to the risk of loss of human life or injury to human beings. So if we take these parameters, we can split these parameters based upon the source and the damage it is causing. So RA is related to the risk of loss of the risk component that is related to injury to human beings. So RA, RB, RC are related to the source S1. That is, if lightning directly strikes on any structure, then it will result in all the three damages. Like if I am residing on a particular building, if lightning is striking on my particular building, then what happens? Obviously, it will result in damage to the structures. So damage to the structures when we covered in R2, that is damage to D2. So RB is the component that is related to the damage of structures if lightning is striking on a particular structure. So if lightning is striking on my building, the chances of the person residing on the particular building will be little higher. So RA is the component that is related to injury of persons on their particular structures. So that is the risk component related to the injury of persons if lightning strikes on a structure. And RC is the component that is related to the failure of electronic equipments inside the structures. So if lightning is striking on my particular building, then obviously the electronic equipments inside the building may also get damaged. So if electronic equipments are damaged, means that will be covered by using the component RC. So from this we can observe that if lightning is striking on any structure, it will result in all the three damages, which are injury to human being, damage to the structure, and failure of electronic equipments. So the first three components are related to the lightning directly striking on a building. And the fourth one, RM, is the component that is related to lightning striking near the building. So if lightning strikes near the building, how it can cause damages? So if lightning is striking near the building, then the surge entire lightning impulse current will be discharged into the soil. So if any cover line or data line is laid underground or near to the point of strike, then the chances of induction will be there. So if lightning strikes near the building, it may result in failure of electronic equipments alone. It won't result in injury to human beings. At the same time, it won't result in damage of structures because it is striking near the structures only. So if lightning is striking near the structure, it will result in failure of electronic equipments if any cable is laid near to the power point of strike. And third one is the lightning striking on the power line. So if lightning strikes on the power line, then it also will result in all the three types of damages. Like it will result in injury to human beings, it will result in failure of structures, and third one, definitely it will result in failure of electronic equipments. So lightning striking on the structures and lightning strikings on the power line will result in all the three types of damages. And fourth one is lightning striking near the power line. If lightning strikes near the power line, then in this case also, because of this induction between this lightning impulse current and the power line or data line near this conductor, the surges might get induced on the power line or data line, and the electronic equipments that are connected to this particular line may get damaged. So if you closely observe this, lightning striking on the power line and lightning striking on the structures will result in all the three types of damages, and lightning striking near the structures and near the power line will result in only failure of electronic equipments alone. So if I take this normal buildings and structures, the R1 is mainly concentrating on injury to human beings. So what are all the parameters that will result in injury to human beings if lightning is striking on the particular site conditions? So if I take normal office or residential building, failure of electronic equipments most probably won't result in injury of human beings. So that is the reason if I am performing this calculation for individual buildings, then I will neglect RC, RM, RW and RZ. So the reason is this RC, RM, RW, RZ are the risk component that is related to the failure of electronic equipments. So in our normal buildings and structures, failure of electronic equipments won't result in loss of human life. So for calculating the value of R1, If it is a normal building, we won't consider RC, RM, RW and RZ, and we will be calculating only RA, RB, RU and RV alone. So the second one, R2, is the risk type of risk that is related to the loss of service to the public. So service to the public, injury to human beings or loss of life won't be resulting in loss of service to the public. So from the from the R1, if I remove RA and RU, that is injury to human being components, I will get the value of R2. R2 is nothing but risk of loss of service to the public, so which covers the substations and the telecommunication industry or gas industry, where if the particular industry get affected, several group of people may get affected. For example, if lightning strikes on any transformer or switch yard, a failure of one particular transformer will result in loss of supply to all the people who are depending upon that particular transformer. So this kind of things will be coming under loss of service to the public. And third one is the cultural heritages. So if you take in India, there are a lot of structures which were constructed before 500 years and 1000 years and all. So we have to provide proper protection to them. So the R3 is mainly focusing only on the physical damages. So among these 8 components, RB and RV are related to the loss of physical damages to the structures. So that is the reason for R3 we will be considering only RB and RV. So if you take this R4 is nothing but this economic losses. So all the type of damages will result in economic losses. So that is the reason we have included all the risk components. So if we understand what are all the each and every risk components, then only it will be easier for us to perform these calculations. So if I am performing this risk assessment for a normal residential building or office building, then in that case, the damage to this particular building won't result in loss of service to the public, and these buildings are not a cultural heritages. So we can neglect R2 and R3. So if I am working on a particular residential building or office building, then R2 and R3 can be neglected unless it is related to this gas industry or substations, like that kind of structures. So for normal residential building or normal office building, R2 and R3 can be neglected. R1 will be considered into the account. So if you take R1, it contains 8 parameters, and among these 8 parameters, we will remove RC, RM, RW and RZ because that are related to injury to human beings due to the failure of electronic equipments. So in normal buildings and all, failure of electronic equipments won't result in loss of human life. So that is the reason we will neglect that. So if I take R1, it contains 4 components that are RA, RB, RU and RV. So these are the 4 components that are related to R1 for a normal building. Okay. So if I want to perform this calculation of a normal building, I will perform calculation only for those 4 parameters. I won't include this remaining parameters. So in which cases we will be considering the remaining parameters. So if I'm working for a hospital building, so in a hospital building, the failure of electronic equipment will result in loss of human life. So if it is a hospital building, then I have to consider RC, RM, RW and RZ. Similarly, if I'm working on an explosive factory and or chemical industry where failure of electronic equipment will result in small sparks and which will result in a huge explosion, for those kind of structures, I have to consider all the 8 parameters. So among these 8 parameters, RC, RM, RW and RZ will be considered only for the structures with risk of explosion and for the hospitals. So this is the formula for calculating the value of risk components. So for example, if it is RA will be ND into PA into LA. So where the 3 components written are number of dangerous events per annum, second one is probability of damage, and third one is consequent losses. So if I consider all these 3 parameters, the first one is number of dangerous events per annum. So the most important parameter is number of dangerous events per annum, which depends upon number of thunderstorm days in a year. So if I'm working on some site conditions where there is no lightning at all, or the number of lightning strikes in a year is very much low, then in that case, the risk due to lightning also will be very much lower. So the first criteria that has to be checked is number of thunderstorm days in that particular location. So based upon that, the risk will be different. And the number of dangerous events also depends upon the dimensions of the building. For example, everyone knows that if my height of the building is much higher, or if my structure is the tallest structure in that particular locality, then obviously risk due to lightning on my particular building will be higher. So the dimensions of the building will be considered in the number of dangerous events and as well as the surrounding environment. For example, if I am residing in a building of G+3 that is around 12 meter height. So if this 12 meter height building is located on a remote area, then my building will be the tallest building. But if the same building is located inside a city limit where my building is surrounded by structures of height around 20 meters or even 50 meters, in this particular case, the dimensions of our building will be the same, whereas the surrounding buildings makes our building much smaller. So the surrounding environment also will be coming into the picture for number of dangerous events per annum. So the parameters considered for this number of dangerous events like thunderstorm days in a year, dimensions of our building, surrounding environment, all these parameters are constant values. We don't have any control over these things. The second parameter is the probability of damage to a structure. So in this probability of damage, here we will be discussing about this. What are all the preventive measures that we can take for reducing the risk due to lightning? For example, if there is no lightning protection system installed on my structure, if lightning is striking, then it will strike on my building and it will result in some losses. If I am installing one lightning protection system by installing air terminal and down conductor and everything, then if lightning strikes, then the lightning will be intercepted by this air terminal and the risk is reduced. So the prevention measures includes installing this air termination system, installing the surge protection devices, and providing this warning notices and all. So that will be coming under the preventive measures. So if I am performing this risk assessment calculation, the modifications that I will make for reducing the risk due to lightning will be mainly on this probability of damage to the structure. So that is the area where we will be having the control. And last one, LX, is the consequent loss. So what will be the losses incurred to the particular structures or site due to the lightning? So that we will be discussing on this consequent loss, which includes what are the, if I'm having any highly inflammable materials or what are all the works that are happening in that particular site, what will be the risk of fire and explosion, whether I'm having any prevention measures or protective measures for reducing the loss due to fire and all. So that will be coming under consequent losses. So these are all the three main components involved in calculating the risk component value. So the first thing is we have to calculate the value of risk component. After calculating the value of risk component, we have to calculate the value of a risk. So this is the formula provided by the standard for calculating the values of different risk components. So the different risk components involved are RA, RB, RC. So for each and everything, they have provided a formula for calculating the risk component values. So if I'm working on normal site conditions, I won't be going for calculating all the values of 8 parameters. Instead, I will be calculating only the 4 values, which are RA, RB, RU and RV. So for normal building kind of buildings, I will be calculating only 4 values, RA, RB, RU, RV, and based upon that, I will be calculating the value of R1. So as I mentioned, one of the most important parameter on which the risk assessment value mainly depends is the number of thunderstorm days. So in this map, you can observe that they have marked the number of lightning strikes on different regions. So if you closely observe this, the region on the right side, that is the West Bengal region, West Bengal, Odisha, Bihar, Patna and Uttar Pradesh, these are the regions which receives more number of lightning strikes in India. So if I am working on certain kind of locations, then I have to take more preventive actions for reducing the loss due to lightning. If the same kind of building is located in Chennai and located in Rajasthan and another one is located in West Bengal, then the risk will be more in West Bengal building than the Rajasthan and the Chennai. So even though building dimensions are same, The risk mainly depends upon number of lightning strikes on that particular region over the year. So this is one of the important parameter that has to be considered while performing this designing. So this is the collection area. So if I am working on this, performing the risk assessment calculation, I won't consider this dimensions of the building alone. So the dimension based upon the dimensions, the area outside the building also will be having some influence. So the area up to which the building or structure is having the influence will be considered as the collection area. So if you closely observe this, the slope is considered as 3 times the height. So if the height of the building is much higher, then the area covered also will be much higher, and hence the risk due to lightning also will be much higher. So practically and theoretically, the height of the building plays an important role in constituting the risk assessment. So the other parameters that are involved in calculating the risk, the first time is, that is number of dangerous events, is structure location factor. So as I mentioned, if my building is surrounded by the buildings which are much taller, then the risk due to lightning on my particular building will be lower. So if my structure is surrounded by higher objects, then the risk value will be lower. That is determined by the value 0.25. So if my building is and other building are of same height, then the risk will be moderate. So the value of CD is 0.5. If my building is located in an isolated area, then the value of CD will be 1. And if my building is located on the hilltop, the risk will be much higher. So that is denoted by the value CD as 2. So from this, we can observe that the value depends upon the surrounding environmental as well. Whether my building is surrounded by taller structures or my building is a taller structure. So that is one of the important parameters. So the next one is line installation factor. So for example, if I am taking my building as an example, for all the equipments, I will be taking this power line from the outside. So how I am taking this power line? If my power line is an overhead line, that is aerial, the probability of lightning directly striking on the power line will be higher, and hence the risk is also higher. But if I am taking this power line through an underground cable, the effect of direct lightning strike is lower, whereas if lightning strikes near this power line, the induction may happen. So that is the reason the value of C is lower if I am taking this buried conductor and higher if I am taking it as an aerial conductor. Next one is line type factor. How this line type is making a difference. So if I am taking a high voltage line, then before the transformer, the first component which we will use is the lightning arresters. That is high voltage lightning arresters. So if lightning strikes on any of this power line, at the point of entry itself, we will be providing a surge arrestor or high voltage lightning arresters for diverting the surges to the ground. Since we are providing a separate surge protection device for diverting the surges, the risk value is lower in high voltage lines, whereas in low voltage lines, we won't be having any separate surge arresters. So the risk will be higher if I am taking LV power, and it will be lower if I am taking this HT power. So the next one is line environmental factor. Whether my building is located in a rural area or urban area. So how this environmental makes an impact on risk assessment. So if lightning is striking on any structure, if my building is located in a rural and isolated area, the entire surges will be traveling to the particular line, and the magnitude of surge that might be entering into my building will be higher, and hence the damage also will be higher. But if my building is located in a city limit, in an urban area, then if lightning strikes on that particular line, there will be more number of parallel paths for the lightning. So from the same line itself, almost 10 to 20 members will be taking power supply. So the surge's magnitude will be reduced. So the damage also will be reduced. So that is the reason, based upon the line environmental factor also, the risk will be varying. So next one is probability of damage. So here, up to the previous slide, we have explained about this, the parameters involved in number of dangerous events per annum, NX. So the second one is the probability. So in the previous slides, all the parameters involved, we don't have any control. For example, here, I don't have any control over the line environmental factor. I don't have any control over the LV power or HT power. So if I want to take HT power, then my demand has to be higher. So I cannot take HD power for lower power demands. So in the previous slide, the surrounding environment, I cannot have any control over the height of the structure surrounding my building. Third, line installation. In some areas, even if you want, I cannot take aerial line. So there are so many practical difficulties involved. So all these parameters are constants and we don't have any control over these parameters. So in the parameters that are related to the number of dangerous events, all the parameters are constant, and once it is determined, we cannot change it. But the next one is the probability. So this is the actual region where we can have the control for reducing the risk due to lightning. So the first one is probability value that is due to shock to living beings due to dangerous step and touch voltages. So for this two sources, that is lightning striking on the structure and lightning striking on the power line, the two important parameters that has to be considered is the step and touch voltages due to this high impulse current. So for protecting the step and touch voltages, if I take the substation, we can have a proper calculation. We know what will be the fault current, and we will be performing this, providing the earth mat for reducing this risk control. But if you take this lightning, we don't have much idea about what will be the magnitude and how can we have the calculations and all. And here the current duration also will be very much lower. So having a tedious calculation will be very much difficult. So the standard has provided different methodologies and prevention measures for reducing the injury to human beings due to the step and touch voltages. So the first one is warning notice. So if I take any power panels, they will be providing a warning like danger 11 kilovolt, danger 22 kilovolt, danger 110 line kV line. So like that, they will be providing a warning notice. So similar to that, if I provide any warning notice for this down conductor, so like danger, don't touch, it is a lightning version conductor like that. So if I'm making a contact, touch potential will come into the picture. So if I don't make any contact, the touch voltage can be avoided. So one of the prevention measures is having warning notice. If I'm providing warning notice, then also accidental contact will be there. So what I can do, the next step is electrical insulations. So by providing this PVC insulation or any other insulation, I can avoid this direct contact. So if I'm providing insulation, then the risk can be reduced to almost 100 times. And the third one is equipotential bonding, and if it is a physical restrictions, by providing any obstacles, if I am avoiding the contact, then if I am providing any physical restrictions, the value of PTA can be even reduced to 0. So this is the parameters that are related to reducing the damage to the human beings by step and touch voltages. So apart from this, the conductor which we are using will be always buried at a depth of around 500 mm. So this will also have some impact on reducing this damage due to the step and touch voltages. So that is the reason we always recommended to bury the conductors of lightning protection system below 500 mm. So if the discharge happens, it won't having much impact on this human beings. So this is the next probability, PB. So here you can observe that for if there is no lightning protection system, the value of PB will be considered as 1. So if my structure is protected by lightning protection system, then in that case, depending upon the level of protection, the value of PB will be different. So for example, while performing the risk assessment calculation, I will be performing the calculation at the first without lightning protection system. So without lightning protection system will be, then I will be substituting the value of PB as 1. If the PB as 1, what will be the value of risk? Then if the risk is higher, if PB is 1, then I will be going for level 4 protection. In that case, the value of PB will be reduced to 0.2. So initially it was 1 and now it is reduced to 0.2. And if the value is still higher, I will be going for level 1 protection. And if I am going for level 1 protection, the value is reducing to 0.02. So initially the value of PB was 1, now it is reduced to 0.02. Since the value of PB is reducing, the corresponding risk component value also will be reducing. So this is how by installing this lightning protection system, we will be reducing the value of risk due to this lightning. So the third one, here also PT also, it will be related to this danger because of dangerous touch voltages. So if that lightning is striking on the power line, so in this case, the touch voltage won't be coming into the picture because that impulse current is traveling only through this power line. So that is the reason here we will be considering only touch voltages, whereas for the first one, PTA, we will be considering both touch as well as the step voltages, because here the lightning is striking on the structure. So we can observe in the type 2. So PTA, that a flashes to a structure will cause. So if lightning is striking on the structure, then both step voltage and touch voltage will be coming into the picture. But if lightning is striking on a power line, then the step voltage won't be coming into the picture, only the touch voltage has to be considered. So if there is no protection measures, then the PT value will be 1. And similarly, if I am having warning notice, the value becomes 0.1. If it is electrical insulation, 0.01. And if it is physical restrictions, it will become 0. And next one, if I am having this electronic equipments, the damage to the electronic equipments can be controlled by installing this surge protection devices. So if I am installing this surge protection devices, based upon the level of protection, the damage also will be reduced. So if there is no SPD, then the value of PEB will be 1. So if I am having this SPD, then if it is level 3 or 4, the value will be 0.05. So you closely observe it. From 1, it is reducing to 0.05. And if I am having this lightning portion level as 1, then the value is still reducing to 0.01, which is 1 by 100. So by installing this SPD at level 1, I am reducing the risk to 100 times. So this is a formula for calculating the corresponding loss. So here if you observe, the different parameters involved are RT, LT, NZ, NT. So I will explain the parameters involved in the next slide. So the first one is the RT. That is the factor related to the type of soil and flow. So if lightning current is discharging, so if the surface layer is having higher resistivity, then the effect of step and touch voltage will be reduced. So in this parameters, we will be considering what is the type of soil, that is the resistivity of soil, and what is the type of flooring which we have. So if it is a normal concrete flooring, the effect will be lower. But if I am having any insulation over this concrete flooring, the effect can be further reduced. So the value parameter RP is nothing but provisions taken to reduce the consequences of fire. So if lightning is striking and if there are any flammable materials there, it will result in fire accidents. So what are the provisions which we take for the preventing this damages? Like if I am installed in this firefighting system, if I install this manual firefighting system, then it will take some time for the particular person to operate this fire quenching mechanism. But if I am installing this automatic sprinkler system, it will automatically quench the fire whenever it senses this fire accident. So if I am having this automatic system, the damages and the losses will be much lower. If I am having manual firefighting system, because of the time difference between the instant of fire and the quenching, there will be some losses. If there is no firefighting system, then the losses will be very much higher. So the RP is the parameter that is related to provisions taken for reducing the consequences of fire. And RF is related to the risk of fire and explosion. So if I am working on certain chemical industries, the risk will be much higher. If I am working on any petrochemical industries, like it will be resulting in huge explosions. So if I am working on normal industries, the risk of fire and explosion will be lower. So if I am working on a petrochemical industry, even a small temperature rise or even a small spark will result in huge explosion. So in those kind of things, the RF value will be higher and the risk also will be very much higher. And HZ is the special resort that is very specific to the particular conditions. NS is the number of persons in the zone. So if you take this risk assessment, we are mainly concentrating on protection to this human beings. So if the number of persons on the particular site condition is higher, then risk also will be higher. If the number of persons is much lower, for example, if you take any solar power plants, the area will be much higher, whereas the number of persons will be very much lower. Only 5 or 10% will be operating for the particular entire plant. So the area will be higher, but number of persons will be lower. So if I take any hospitals and all, the area will be lower, but number of persons will be higher. Also, if I take any schools or colleges, the same is applicable. Area might be lower, but the number of persons will be much higher. So if I am considering the damages or injury to human being, if the number of persons is higher, the risk also will be higher and losses also will be higher. So the last one is period of stay. For example, if you take schools and colleges, if lightning is striking at the midnight, there won't be any person in the particular campus and the losses will be very much lower. But if I take any industries which will be operating 24/7, then the damages, if lightning striking on the night, will be almost equal to the damage that is caused in the daytime. So that is related to the time parameter T. So these are all the different parameters involved in calculating the risk due to lightning. So this is a kind of special hazard. The special hazard depends upon the number of people and the difficulties related to the evacuation. If the number of persons is much higher, then there will be a high level of panic. If there is no special hazard, if it is a normal building, then the value of HZ will be considered as 1. And this is the values that are related to LTLF and LR for different losses. So this is what I explained related to the resistance for reducing this damages due to the step and touch voltages. So if it is agriculture and concrete, the value of 40 will be 10 power minus 2. If it is a wood or asphalt or aluminum, the value will be 10 power minus 5. So depending upon the material which we are using, the value will be different. And the value of RP is the preventions which we take for reducing the fire. So there is no provision, RP will be 1. And if I am having this manual firefighting system, the value will be 0.5. If I am taking this automatic sprinkler system, it will be 0.2. So these are all the parameters which we normally consider for performing the risk assessment calculations. So after performing this calculation, I will be calculating the value of RA, RB, RU and RV. If I add all these four parameters, I will be getting the value of R1. Then how can I consider whether it is safe or not? I have to compare the value of R with RT, that is the tolerable risk. So if the value of R is lesser than tolerable risk, the building will be considered as safe. If the value is greater than tolerable risk, the building is unsafe. So our motto is we have to bring down the value of risk below the tolerable value. This is the procedures involved. So first one is we have to identify the components that are related to the risk. So there are 8 different components involved, but we won't consider all the 8 different components. We will be considering only the 4 components RA, RV, RU and RV for normal kind of buildings and office buildings. So first thing is we have to identify what are all the risk components that are applicable to our site conditions. Second one is we have to calculate the value of each and every risk components. And third one is we have to calculate the value of risk, and I have to compare the value of R and RT. And if the value of R is lesser than RT, the building will be considered safe. So this is the flowchart provided by the standard. So here you can observe that we have to repeat the cycle till the value of R becomes less than RT. So first I will be performing the calculation without any protection measures. If the value is greater than RT, then I am going for level 4 protection. So in the probability of damage, I have shown how the values are changing if I am changing the level of protection. I am just going to the slide. So if you observe in this, so if I am going for without lightning protection system, the value of PB will be 1. If I am going for level 4, the value will be 0.42. So if I am performing the calculation with the level 4 protection, I will be substituting the value of 0.2 during the calculation. And if I am working with level 1 protection, I will be substituting 0.02 for this calculation. So this is how, by installing this external lightning protection system, we are reducing the risk due to this lightning. So I have to repeat this calculation until the value of R becomes lesser than RT. If the value of R is lesser than RT, then the risk due to lightning will be lower on that particular structure. So if I am performing the calculation and even without any external protection measures like installing a lightning protection system, if the risk due to lightning is lower, in that particular case, lightning protection system is not mandatory for my building or structure. So if lightning protection system is not mandatory, which means that even if lightning strikes on my structure, the damage will be lower, we can manage. But it does not mean that if the value of risk is lesser than RT, the lightning won't strike on the structure. Even if the lightning strikes, then the damage will be lower. So that is what it means. So if the risk is lesser than RT, so there won't be any lightning strikes on my building, we cannot consider it like that. Even if the lightning strikes, the damages to the lightning will be much lower and it will be manageable. So for performing this calculation, these are the details which we require from the customer side. So first one is the building dimensions, layout details, and is there any existing system present or not? What is the level of the system they have installed? Or what is the purpose of building? Because if it is a chemical building, the risk will be higher, risk of fire exposure will be higher. If it is a residential building, it will be lower. and what will be the total number of people, Google coordinates. So these are the inputs which we receive from the customers for performing the risk assessment calculations. So I am just attaching a screenshot of this calculation. So first thing is I have to perform the value of each and every risk component. So here I have shown the calculation for RA and RB. So the value of RB contains three parameters. One is ND into PA into LA. So ND is the value of ND is coming around 0.31, and the value of PA contains two parameters, PTA and PB. So both the values are what? So the PB is considered, and the value of NA is also calculated by performing the formula provided. So if I perform like this, the value of RA is coming around 3.91 into 10 power minus 8. Similarly, I am calculating the value of RB. RB is the parameter that is related to the damage of structures, whereas RA is related to injury to human beings. So if I am going for RB, the three parameters involved are ND into PB into LB. So ND into PB are common, which we know used for this RA exams, and the third parameter is the LB. So if I perform calculation for LB, the value is coming around 1E minus 2. So if I calculate the value of RB, it is coming as 10 power minus 3. So among these two parameters, you can observe that RA is e power minus 8, RB is e power minus 3. So if I calculate R1, it will be sum of four parameters, RA plus RB plus RU plus RB. Since RB is in terms of 10 power minus 3, obviously the value of R1 will be also higher. So the risk due to lightning will be much higher on this particular building without any protection measures. So here we have considered the value of PB as 1 because I have considered there is no lightning protection system involved. So this is the value for the different parameters. So here you can observe that the value is much higher. So the risk due to lightning is much higher on this particular site conditions. So if I want to provide protection, then what I have to do? I have to install lightning protection system. So if I am installing this lightning protection system, then what will be the value of PB? PB will be becoming very much lesser, like 0.02. So since the value is reducing, the value of RB will be reducing. If the value of RB reduces, then obviously the value of RA will be reduces. So this is how, by providing this preventive measures, we will be reducing the risk due to lightning. And one more thing which we have to notice. So here we have mentioned additional protection measures, PTA and PTV. So PTA, there is no protection measures we have provided. So if I want to reduce further, like protection measures involved, which includes providing warning notices, electrical installation and all. So by providing this additional protection measures also, I can bring down the value of risk. So by performing this kind of activities, how I can reduce the risk due to lightning below the tolerable value. So our ultimate aim is we have to bring down the value of risk like R1, R2, R3, R4 below the tolerable value. So the tolerable value the standard has provided. So by performing this calculation, so we have to repeat this calculation. So here I have performed the calculation with the PB is equal to 1. So second, if I am going for level 4, I have to perform the calculation with 0.2. Again, if the value is higher, then I have to going for repeat the calculation with level 3. Then if the value is higher, again I have to perform the same calculation with the PB is equal to 0.02, which is for level 1. So our ultimate aim is we have to bring down the value lesser than the tolerable limit. So this is how we have to perform this risk assessment calculation. And after making this modifications, we have to note down what are the modifications which we are making. Like we have considered automatic fire fighting system. We have considered lightning protection system at level 1. We have considered surge protection devices at level 1. We have provided additional protection measures of providing electrical insulation for physical restrictions. So if I am providing physical restrictions, the value will be dropping to 0. So by providing this kind of activities, we are bringing down the risk due to this lightning in the form of step and touch voltages. So this is how we have to perform the calculation, and our ultimate aim is we have to bring down the value of R lesser than the RT. So the second one is designing of lightning protection system. So in this previous section, we have explained about the risk assessment calculation. And the final output of the risk assessment calculation is whether the lightning protection system is required for the building or not. So the second one is based upon that we have to perform the calculation, and in this designing phase we will be considering the output of the previous stage, like whether lightning protection is required or not. If required, what will be the suitable level? That will be the output of risk assessment. By considering that, we will be performing the designing of lightning protection system. So, if I am performing the designing of lightning protection system, it majorly contains three main components. And the three components are air termination system, down conductor system, and earth termination system. So, the air termination system is the component which intercepts the lightning, down conductor system which acts as a bridge between air terminal and down conductor, and earth termination system dissipates this energy into the soil. So, we have to perform designing for all these three components, and most importantly, the first component, air termination system designing, mainly depends upon the level of protection. So, the standard has explained about three different methodologies for performing this designing of lightning protection system. So, these three methodologies are called as air termination placement methodologies. So, the air termination placement methodologies, which means how to determine the position of air terminals. For example, if my building is of height, length and width is 50 meter cross 40 meter. So, if it is 50 meter cross 40 meter, then how can I determine the location of this particular air terminal? So, if 5 air terminals are required, and what will be the position of each and every air terminal? That can be determined by using this particular placement methodologies. The different placement methodologies are mentioned by the standard are protection angle method, mesh method, and the rolling scale method. So, among these methods, we have been using this protection angle method for a long period. Like, if I take this olden designs, it will be having one rod at the top of the building, and this rod will be provide some protection up to certain angle. So, since the protection is depending upon the angle, it will be considered as protection angle method. And the second method is mesh method. Mesh method will be simply laying the conductor in the form of mesh over the structure to be protected. And third one is the rolling scale method, which is we are using commonly nowadays. So, these are the commonly used methods for designing.
So, something.
So, this is protection angle method. So, from the name itself, we can observe that the protection mainly depends upon the angle. So, if you closely observe, the angle depends upon level or the height of the air terminal. So, if we observe this angle on two sides of this air terminal at the corner, you can observe that the angle is different on both the sides. So, the angle is depending upon the height above the reference plane. So, if the height of the air terminal is from 2 meters above this terrace, then I have to consider the angle for 2 meter height. And if I have to consider the height on the left side, then I have to consider the height of the building also. So, if the building height is 10 meter, then the overall height will be around 12 meter. So, this is the graph provided with the standard for performing this calculations. So, from this graph, I have to take the value of angles. Like if it is 2 meter, I have to extend a line from 2 meter, and for 2 meters, what will be the particular angle for this particular site condition. So, if it is 2 meter, if I go for level 1 protection, the angle will be 70 degrees. So, if I am extending the line up to level 4, the value will be coming around 78 degrees. So, from this graph, I have to take the value of angles. From the angle, I have to calculate the value of radius of protection. So, the angle we can use this tan theta formula. So, we know that tan theta will be opposite side by adjacent side. So, in our case, the theta is from the top of the air terminal. So, from A to C is this angle. So, if I take like this, then from this tan theta formula, I can calculate the radius of protection. We know the height of the air terminal, and from the graph, we know the value of theta also. We have to use tan theta formula. From this tan theta formula, we have to substitute the value of height and the theta, and we can calculate the radius of protection. So, we have already done this calculation, and we have arrived at a result for different heights. So, here you can observe that for 5 meter height at level 4, the radius of protection will be around 16 meters. So, similarly, if I am going for 15 meter, I have to extend a line from 15 meter, I have to find the angle, and from that angle, I have to calculate the radius of protection. So, the second method is mesh method. So, in mesh method, we will be placing the conductor in the form of mesh over the structure to be protected. And here also, if you observe, the mesh size depends upon the level of protection. If I am going for level 1 protection, it will be 5 cross 5. If I am going for level 4 protection, it will be 20 cross 20. Here, there won't be any vertical air terminals. The conductors will be buried over, will be placed over the structure to be protected in the form of mesh. So this one is the problem with mesh method. So nowadays many people are not going for this mesh method because of the rooftop solar installations. So if we are installing solar on the rooftop, then the height of the panels will be higher than the mesh conductor, and the panels will be placed over this mesh conductor. So the structures won't be protected by this mesh conductor. So even if I want to install, if I want to protect this building after installing solar, then I have to modify the design by installing this vertical air terminals by using either protection angle method or rolling sphere method. So the commonly used method is the rolling sphere method. Here we will be rolling an imaginary sphere over the structure to be protected, and we need to ensure that the sphere does not make contact with any part of the building. Here also, the radius of sphere will be depending upon the level of protection. So for level 4, it will be 60 meters. So we have explained in detail about this, all the calculations like protection angle method and rolling sphere method in a separate webinar video. So you can go through the particular video for detailed calculations. Here I'm just providing an outline. So if I want to calculate the distance between two air terminals, then I can use the second formula. D is equal to 2 into square root of 2pr minus p square. So it includes two parameters. One is radius, which depends upon level of protection, and second one is the penetration distance. So penetration distance is nothing but the distance up to which the sphere goes below the level of air terminal. So you can observe from the above image. So the penetration distance is marked as the distance where the bottom portion of the sphere is coming below the level of air terminal. So if I increase the distance, penetration distance also increases. If I increase further, then at one particular point, what happens? The sphere will make contact with the structure to be protected. So here you can observe. So if I increase the distance between the space between the air terminal, more portion of the sphere will be coming below the air terminal. So if I increase further, then the center point will be making contact. If the center point making contact, then the particular portion will be considered as unprotected. So we have performed the calculation using the formula provided for different heights, 0.5 meters, 1 meter and 1.5 meter. So based upon this calculation, we have to place the air terminals accordingly. So here the distance provided are the maximum distances. So it is not the actual distance, it is the maximum distance that has to be provided between these air terminals. So if I am performing this air terminals in the form of a rectangle, then if I take this rectangle, then the maximum distance will be the diagonal distance and not the length or width of the air terminals. So for example, if I take this rectangle of size 12 cross 9, so if I measure the length, it will be 12 meter. If I can measure the width, it will be 9 meter. But if I measure the diagonal, the diagonal will be around, it will be a 15 meters. So if I roll this imaginary sphere along the diagonal direction, then the sphere will be making contact. So it is in the diagonal direction, the building is not protected. So if I want to provide protection, means the maximum distance should be maintained along the diagonal. So the next important is the surge protection devices. So from these slides, we can observe that we have to go for, if I am going for vertical air termination system, then these two methodologies, protection angle method and rolling sphere method, can be used. And it is not mandatory that I have to go for only protection angle method or I have to go only rolling sphere method. So based upon the site conditions, we can determine which method will be suitable for our site conditions. So if I am going for this rolling sphere method, here also it is not mandatory that I have to go for 1 meter air terminal. So based upon the site conditions and based upon the designing, I can decide whether I have to go for 1 meter or whether I have to go for 2 meter or whether I have to go for 3 meters. So if I am going for 3 meter air terminal, then the distance between the air terminals will be much higher and the number of air terminals will be very much reduced. So it is up to the designer to decide whether we have to go for 0.5 meters or 1 meters or 1.5 meters. So if the same layout is provided to different designers who are performing this risk assessment and designing calculations, the output result which we are designing won't be the same, because based upon the position of the air terminals which we are using and the height of the air terminals which we are using for this calculation, the number of air terminals will be different. So even though the rebuilding dimensions are the same, if different people are performing the designing, then the number of air terminals and the parameters like height of the air terminals won't be the same. So if I'm performing the calculation and using 1 meter height of air terminal and arriving at 10 number of air terminals, and if one more person is performing the calculation for 2 meter of air terminal and arriving at 5 numbers of air terminal, then both the designs are correct. So we cannot tell that I have to go for only 1 meter or I have to go for only 2 meters. So it is up to the designer and it is up to the site conditions to decide what will be the suitable height of the air terminal for the particular site conditions. So standard does not stick to for any specific requirement like I have to go for only 1 meter above the structures or 2 meter above the structures. So we have performed designing for certain site conditions where for the particular site condition we have used a 5 meter air terminal by providing additional support. So it is up to the designer and it is up to the site conditions, because for particular distance I cannot place any air terminal. It is completely shielded, I cannot place any air terminals by providing holes. So that is the reason we increase the height to 5 meters so that the distance will be much higher and there is no need for providing air terminals in between. So it is up to the designer to decide the level of, decide the height of the air terminal. So based upon the height, I have to vary the calculations and I have to maintain this. And the most important thing that we have to keep in mind in performing the rolling square design calculation is, here we are calculating the maximum distance between two air terminals. So the distance between the air terminals and the diameter of protection will be different. In protection angle method, we will be calculating the radius of protection, but in this particular method, we won't be calculating the radius of protection. So here I cannot divide this value like 15.46 by 2 and mention that the radius of protection for 0.5 meter air terminal is 7 meters. I cannot mention like that because here the protection is provided by the cumulative effect of two air terminals. I cannot divide it by 2 for calculating the radius of protection provided by one air terminal. So then we have to keep in mind. Also, if I am performing the calculation using different methods like a protection angle method and rolling square method, obviously the number of air terminals required will be different because it is completely different methodologies. So it is some enhanced method. So there will be some difference in the number of air terminations also. So the most important thing nowadays many people are facing is surge protection devices. So many people will complain that there was no lightning strikes recorded in my region. So even though there is no lightning strikes recorded, my electronic equipment inside the building was failed. So that is the commonly raised question by many people. So the reason is, even if lightning strikes are away from your building, because of this indirect effects, like I have mentioned about two sources, like lightning striking on the power line and lightning striking near the power line. Even though if the lightning is striking somewhere away from the building, the electronic equipment inside the building may get damaged. So if I want to provide protection means I have to provide suitable surge protection devices. So here you can observe that the first one is the lightning conductor. So if I'm having a lightning conductor and instead of this panels, if I'm having any power line or data line, then obviously the magnetic field produced by this power line and data line will be having an impact on this power line or data line. So if the surges is having some impact, there is EMF is induced, means the electronic equipment connected to the particular power line or data line will get affected. So to avoid this, you have to go for the surge protection devices. So in this image, you can closely observe that the electronic equipment got damaged and below this electronic component, there was a fuse provided. So even though we have provided the fuse, the electronic component was not protected. The actual reason is the damage was caused because of the surges. The fuses won't provide protection for the surges that are due to lightning. So the fuses, MCB and circuit breakers and the voltage stabilizers which we are having won't provide protection to the electronic equipment due to the surges. So that is the reason we have to go for a separate device. So these are the damages caused due to this lightning impulse surges. So it is very dangerous similar to this normal lightning damages. So we have to provide proper protection because nowadays we are using more sensitive devices. If these sensitive devices are not protected properly, then it will result in huge loss. So the damages caused by surges are mainly classified into three types. One is interruption of operation, second one is damage of components, and third one is deterioration of lifetime. So the interruption of operation means if the equipment gets turned off, if I turn it on again, then it will work normally. And the second one is the damage of components. So the image shown is related to damage of components. And third one is the deterioration of lifetime. So if the magnitude of surge is much lower, then even though if the damage is not caused, then the lifetime of the component may get reduced. For example, if I'm having one equipment which is proposed to have a lifetime of 5 years, then over a period of time, if the continuous surges of very low magnitude is continuously approaching, then the lifetime of the equipment will be reduced from 5 years to 3 years. But the reason cannot be understood because the magnitude of the surges is very much lower. So this very low magnitude surges are always considered as silent killers of electronic equipments. The surges which we mentioned are nothing but very high magnitude but very low duration pulses. So high magnitude, low duration pulses are considered as surges, and it will be in the terms of either 8 by 20 microseconds or 10 by 350 microseconds. So since the duration is very much lower, we have to go provide separate devices. So the MCB will be operating only for 3 to 5 cycles. After 3 to 5 cycles, we will be having some definite time interval. It is not an instantaneous device. So the MCBs and fuses won't be operating, it won't be able to sense the surges. So that is the reason you'll be going for a separate device for surge protection devices. So the surge protection devices are nothing but fast acting switches. So and it will be normally acting as an open switch at normal operating condition. If any surges are approaching and if the voltage is above the threshold limit, then the switch will be acting as a closed switch and diverts the surges to the ground. So during the particular portion, the switch will be acting as a closed switch, and if the surge magnitude is resumed to normal, the normal supply will be resumed to the equipment. So for the particular duration, the equipment won't be receiving any power supply because the energy is diverted to the ground. But we cannot feel the switching because it is taking place for microsecond duration. So in general, in simple terms, this SPDs are nothing but fast acting switches which diverts the surges to the ground. And these are the different types of surge protection devices. So if it is type 1 SPD, then it will be tested for 10 by 350 microsecond. If it is type 2 SPD, it will be tested for 8 by 20 microsecond. And if it is type 3 SPD, it will be tested for 1.2 by 50 microsecond and 8 by 20 microsecond. So these kind of damages can be avoided by providing the suitable surge protection devices. So since there is no surge protection devices, the surges has entered and it has damaged this electronic equipment. So if I have provided any surge protection devices prior to this equipment, then the particular surges might get diverted to the ground and this particular equipment might be saved. So the cost of surge protection devices will be much lower when compared to the loss of cost of this particular building. So nowadays we are going for this automation which involves more sensitive devices. So these sensitive devices are sensitive to even small magnitude of surges. In order to protect this equipment from surges, and if we want to ensure this in uninterrupted operation, then surge protection devices become a very essential part for today's electronic equipments. The surges has been in picture for a longer time, and lighting is also there for a longer period. But nowadays, many people are understanding the importance of surge protection devices mainly because of the usage of more electronic equipments. In the earlier days also surges was there, but the number of sensitive devices which we used was not that much higher. But nowadays, we are even going for home automation where all the electronic equipments in the houses can be controlled using mobile applications. So the size of the equipment is also reducing and the sensitivity of the devices are keep on increasing. So these highly sensitive devices makes the surge protection devices very mandatory for today's building. We have worked with certain projects where for even residential buildings, they have provided a separate surge protection device for each and every panel rooms for protecting this electronic equipment. So we worked with one project where they had turned on the particular TV, where they have procured one TV for almost 14 lakhs. So they turned on the TV after installing this surge protection device. So they waited for 1 week for installing the surge protection device, and after that only they turned on this particular TV. So if we install the surge protection devices, these kind of damages can be avoided. So here you can closely observe that the fuse does not got blown. So if the purpose of fuse is to protect this electronic equipment from the surges also means the fuse might have blown, but here the fuse is not blown and the component got damaged. So from this we came to understand that the damage is caused not because of this power frequency supplies, whereas the damage is caused mainly because of the surges due to this line. So if surges is approaching, the fuses or MCBs which we are providing won't be operated. So that cannot be protected. The equipment cannot be protected by the fuse or MCB or stabilizers which we are using because the sensitivity is not that much higher. So from this damage and from the fuse we understood that the damage is caused mainly because of the lightning impulse current, and at the same time, they have ensured this lightning protection system for this building also. And the number was defined on the lightning event counter. So from the counter, the initial rating was around 12. And after this failure, they checked the counting, it was around 13. So from that, they confirmed that lightning happened on that particular building. And after that lightning happening only, the failure happened. So during the lightning, because of some kind of induction, the surges entered into the particular equipment and the equipment got failed. So this kind of failures can be avoided by installing the suitable surge protection devices. So the surges has been in existence for a longer period, but now we are understanding the importance mainly because of the sensitivity of the devices which we are using nowadays. So the final topic is earthing. So we recently worked with one site conditions where they have used this GA earthing thread. So, but the actual design provided by the consultant was they provided recommended copper strip. But because of the cost constraint, they replaced this copper strip with GA strip. So, before entering into that, let's just provide a small introduction about earthing. The purpose of providing earthing is to divert this fault current or lightning impulse current to the ground during this abnormal conditions by providing a dedicated low resistance path. So if I'm providing this connection to the equipment body, it will be considered as equipment earthing or body earthing. If I'm connecting this earthing to the neutral of a transformer, it will be considered as system earthing, because system in neutral, it will be a live pot. So when connecting the current carrying conductor, it will be considered system earthing. So if I'm providing system earthing, the fault current has to be considered in. So and if the fault conductor sizing is not proper, the conductor may melt and broke. So we have to select the conductors accordingly. So for one of the projects, the consultant mentioned 50/6 copper strip for the particular transformer earthing, but what they did was, since the conductor sizing is same, they replaced this 50/6 copper strip with 50/6 HCGA strip. So the conductor cross-sectional area is the same. So they mentioned that we have mentioned the same area. But what is the parameter which makes a difference? Let us consider the difference in the current carrying capacity. So the main purpose of this electrode which we are using is to dissipate the fault current. So if I'm having the earthing, the current starts dissipating into the soil, and the moment it enters into the soil. But before this current is entering into the soil, the entire current will be flowing to the particular conductor alone. So the conductor should be able to withstand the current, and if it withstands, then only the current can be dissipated into the soil. So if I am not providing proper conductor sizing, then the conductor itself will break because of the huge heating. As we know, the power loss will be there, heat loss, I squared R will be there. If the current member is higher, then more amount of heat will be produced, and because of the more heating, the conductor will melt. So the standard has provided the formula for calculating the current carrying capacity. So this is the formula. From this you can observe that I is equal to SK by root T. So the three parameters involved are cross-sectional area, the parameter K, constant K, and the third one is duration T. So whenever we are mentioning this fault current, we should mention always with the duration. For example, 20 kA for 1 second, 25 kA for 3 seconds, 40 kA for 1 second. So the fault current should be mentioned along with the duration, because depending upon the duration, the fault current level, withstand level also will be changing. So from this, we can observe that the two other parameters are cross-sectional area, and another one is factor K. So the K depends upon the material and the duration. So I have provided the table from IS 3043. So here I have shown the comparison for IS 3043. So here you can observe that they have provided for copper, aluminum, and steel. And they have provided the value of K for 1 second as well as to 3 seconds also. So for copper, the value of K will be 205 for 1 second, and for steel, the value will be 80 for 1 second. Whereas for 3 seconds, for copper it will be 118, for steel it will be only 46. So the value of K itself will be different for the different time period. So I am just showing the calculation for the copper strip and the steel strip. So if I take 25/3 ohm as a copper strip, and for 1 second, the dimension cross-sectional area is the same and the duration is also the same, whereas the value of K will be different for copper and steel. So if I am going for copper, the value will be 205, whereas for steel it will be only 80. So that will be around 2.6 to 2.7 times difference. So if I perform this calculation, I can find that if I'm going for 21/3 copper strip, it will be having a current carrying capacity of 15 kA for 1 second, whereas for steel strip of same dimensions, it will be only 6 kA for 1 second. So in this particular site conditions, they have used a 50/6 copper strip. So instead of 50/6 copper strip, they have used only 50/6 GA strip. So if I take this formula into account, so the fault current rating for 50/6 will be around 61 kA. Whereas if I am going for GA, it will be only 24 kA. There is a huge difference in the current carrying capacity. So if I am changing the material from copper to GA, then I should not consider the cross-sectional area. Whereas I need to consider only the current carrying capacity of the particular conductor which we are using. So if I want to change the material from copper to GA, then I have to find the suitable material sizing, like what will be the suitable size of GA that will be able to withstand this fault current of 61 kiloamps. So from this table, you can observe that if I'm going for 75/10, then for the current carrying capacity of GA will be around 60 kA. So this is the current carrying capacity using the formula mentioned in IS 3043. But in IS 3043, they have provided the constant everything related to the steel. But if I take GA, it will be hard galvanized steel where the coating of zinc will be coming into the picture. So in IS 3043, they have not provided much in detail about this zinc coating and what will be the effect of zinc coating. So we have referred another standard called VL 467 and IEEE 80 for calculating the current carrying capacity of coated materials. So IEEE 80 has mentioned the different parameters related to current carrying capacity of coated materials. So this is the parameters provided by IEEE 80 related to coated material. So the zinc coated steel rod is nothing but the parameter related to zinc coated as in GAs. So whenever we are performing the calculation, I have to calculate this. So by using these parameters, if we perform the calculation, then the conductor sizing has to be 75/12. So if I use 75/12 over GA, then only it can have a current carrying capacity of 61 kA. So if I want to replace this copper conductor with the GA strip, then I cannot go for this equal dimensions, like 50/6 of copper cannot be replaced with 50/6 of GA strip. So if I want to go for the replacement, then I have to replace the 50/6 of copper strip with 75/12 mm of GA strip. So for replacing the earthing conductors, the cross-section area should not be considered, whereas the current carrying capacity of the conductors should be considered. So the conclusion of today's session is the first one is risk assessment calculations. So there are so many parameters involved in performing the risk assessment calculation, and by randomly we cannot select what will be the suitable level of particular site condition. So customized calculations should be performed to determine whether lightning protection system is required for the particular site or not. So if the value of risk is lesser than RT, if the value of risk is less than RT without lightning protection system, then which means that lightning protection system is not mandatory for the particular site conditions. So if the lightning protection system is not mandatory, which does not mean that lightning won't strike on the particular buildings and structures. Even if the lightning strikes, the risk due to lightning will be lower on those particular site conditions. So for additional protection, if we need, we can install the level 4 protection. And based upon the risk assessment calculations only, we have to perform the designing of lightning protection system. And depending upon the site conditions, we can select either rolling spear method or protection iron method or mesh method. But because of this rooftop solar installations, many people are nowadays not going for mesh method. And the two commonly used method are protection iron method and rolling spear method. Among these two methods, rolling spear is more preferred because of these advantages. And the standard does not mention that I have to go for only 1 meter height of air terminal or 2 meter height of air terminals. Based upon our requirements, I can increase the height and perform the calculations accordingly. And because of the increasing sensitivity of the electronic devices, the surge protection devices are nowadays becoming very mandatory. And if I want to provide protection to these electronic equipments, then the MCBs and fuses and voltage stabilizers which we are using won't be sufficient. So we have to go for a separate devices called as surge protection devices. So these surges are called as silent killers of electronic equipments. So these low magnitude surges are very much dangerous, and it may result in reduction of lifetime of the electronic equipments. And most importantly, if I'm going for earthing, if I want to change the material from copper to Ga, then I cannot match the cross-section area alone. So I have to perform this current carrying capacity calculation. So if I want to change the material from copper to Ga, I should not match the cross-section area. So I have to check what will be the suitable size of Ga that will be able to carry the same current as that of copper. Oh, thank you. Any queries?
Anybody?